Hello, this is a video recording for the Physics P1 Energy Transfers topic. First task is to have a go at these starter questions here. So can you list the different types of energy and can you give an example of each of where we might find them? If you are struggling or not sure, then there is the first letter for each energy type there. One of them can have an alternative letter. So where you've got T, that could potentially be an H. And if you manage to finish that within 2 minutes that you can give yourselves, then please have a go at the star task. So describe the energy transfer for a cyclist going down a hill. Please pause the video there for 2 minutes, have a go activity, and then resume when you have completed it. So we should have had a go, and hopefully you have managed to remember all the different energy types that are here. So you've got your kinetic energy, which would be your movement energy. So anything that is moving has kinetic energy. So you can mention somebody running, a car that's moving, somebody on a bike, anything like that. You've got thermal, which could also be put down as heat energy as well. So anything that has that heat energy or thermal or produces it would be considered to have thermal energy. So for example, like a radiator, that would be an example. Light. Another example, so anything that gives off light, so such as a light bulb, when it is switched on, then that would be an example for that. Gravitational potential energy, anything that has a height has gravitational potential energy. So anything that's got a height above the ground, so for example, a rock over the cliff edge, or if you've got a skydiver in the sky at the time, they would have gravitational potential energy. Chemical energy, that would be, for example, a battery or your food, that would contain your chemical energy. Sound, so me talking to you just now or listening to this through a loudspeaker, that would be your sound energy. Elastic potential energy, examples of that would be, for example, a hair bobble or an elastic band or a bungee cord, for example. So those would be all examples of elastic potential energy. You have electrical energy as well. So you have maybe, for example, electricity going through your wires. You plugged your computer in, for example. That would be an example of electrical energy. And then you also have your nuclear, so your nuclear power stations, that would be part of your nuclear energy as well. Just a key point to make here, when you're writing down the gravitational potential and elastic potential energy, make sure you don't forget that word potential as well. If you did the star task, describe the energy transfer for a cyclist going down a hill, then hopefully you've started off with your gravitational potential energy, which is then transferred into kinetic energy. If you have also written, for example, maybe some of that transfer would have gone also into sound and maybe thermal, then you would be correct as well. If you said friction at all, remember friction is a force. It is not a type of energy. So just be careful with that answer. So now you're going to have a go at this exam question. So the diagram shows a cyclist riding along a flat road, and you have to complete the sentence and you need to choose your answers from the box. So as the cyclist accelerates, so they're getting faster, the something energy store in the cyclist's body decreases and the something energy of the cyclist increases. So pause the video here and have a go at that question, please, before moving on. So just going through the answers, you should have got, as the cyclist accelerates, the chemical energy store in the cyclist's body decreases and the kinetic energy of the cyclist increases. So the chemical energy store is transferring from that chemical energy, so that'll be from the food that they've eaten, to transfer into the kinetic energy, so the movement energy for the cyclist to move the legs, which then would move the pedals of the bike. So here's another exam question for you to try. The questions are on the next slides, but you will need to refer back to this for this section. So the image below shows a student before and after a bungee jump. It says that the bungee cord has an unstretched length of 20 metres. So before, the student's on the bridge with the bungee cord, and after there is the extended bungee cord, and the student is at the lowest point possible and they are stationary at the after. So the student jumps off the bridge, You need to complete the sentences to describe the energy transfers, and you've got options to pick from the box. So before the student jumps from the bridge, he has a store of what type of energy. When he is falling, the student's store of what type of energy would increase as they are falling. And then when the bungee cord is stretched, the cord stores energy as what type of energy. So think about at the top, when they're on the bridge, they're at a height above the ground, so what type of energy would that be? As they are falling, that is them moving, so what type of energy would that be? And then when the bungee cord is stretched, what type of energy would be in a stretched bungee cord? So thinking about the stretchiness of it and what that might link to. So here are your answers. So you should have got that from the bridge they have a store of gravitational potential energy. When they are falling, the student's store of kinetic energy increases, and then the cord would store that energy as elastic potential energy. So now here's a bit of a recap to your kinetic and potential energy stores and equations. So you've got the first equation is your kinetic energy is a half times by your mass times by your velocity squared. Second equation is your gravitational potential energy is equal to your mass times by your gravitational field strength times by your height. And the last one is your elastic potential energy is your half times by your spring constant times by your extension squared. So just don't forget when you are having a go at these questions about that square that is there or the half that you have in front. It tends to be a common thing that they tend to forget to put it in the calculator. If you wonder what gravitational field strength is, that's to do with the force of gravity, how much gravity there is on an object for each kilogram of mass of that object. Usually in the question they will tell you what to use for that value. So here is an example question. We're giving you the equation to use, so you just need to practice using it correctly. So you have the mass of the cyclist is 80 kilograms. The speed of the cyclist is 12 meters per second. Calculate the kinetic energy of the cyclist using this equation. So you need to decide which number do you think is your mass and which number is your speed. Just remember, don't forget about that square. Pause the video now, get your calculator, have a go at this question, and then play it again when you are ready to see what the answer is. So here we go. Here is your answer. So your kinetic energy is your 0.5 times by the 80 kilograms. So you remember 80 kilograms would be your mass, and then the speed is 12. You've got to make sure you square that before you use it in the rest of your equation. You should get an answer of 5,760 joules. So on this slide here, we are looking at the relationship between kinetic and potential energy. So if you look at the animation, when the roller coaster is at the top, that's where it'll have most gravitational potential energy. That gravitational potential energy will then transfer into kinetic energy. But throughout the journey of that roller coaster, the gravitational potential energy and kinetic energy will always equal a total amount of energy. You will never have more energy than what you started off with. This is because energy is never created or destroyed. So it can't just come out of nowhere, it can't just disappear. It's got to transfer from one type to another. One thing we've not considered within this animation is the loss of energy due to its surroundings, for example, such as thermal energy. And that would be due to the force of friction. If you like, there is a link at the bottom left to a little animation. It's called FIT, Physics Skate Park, which you can play around, and you can play around with an animation yourself and look at the relationship between the kinetic energy and potential energy. On this slide, I have taken some screenshots of what those animations would look like. So at the top left, when the skateboarder is right at the top of the ramp, you see that where the yellow bar is, that's the total amount of energy that they have, and that will match their gravitational potential energy. So that will be the most energy that they will have throughout their journey. If you go to the image at the top right, then that total gravitational potential energy that you had, well, as they decrease in height, that gravitational potential energy transfers into your kinetic energy. And you can see that their kinetic energy is increasing, so they are gaining speed as they get down to the bottom of the ramp. And then the bottom left picture, when they are at the bottom of the ramp, they have no gravitational potential energy because they don't have a height anymore above the ground. It is all transferred into kinetic energy, and they have the same amount of kinetic energy as they did at the start with the total energy. So you can see that there. The image at the bottom right, that's a little bit different because this is including some of the energy which is lost into its surroundings. So this is where it's adding the force of friction into it. So for example, with the wheels on the ground, we have a force of friction. And so as they've gone down the ramp, their gravitational potential energy, which they would have had the same amount to start off with, has transferred into kinetic energy, but also thermal energy. Okay, so eventually what will happen is they will not go to the same heights they were before, they will gradually get lower and lower as they go back and forth across both sides. And then eventually the skateboarder will come to a stop. Okay, so what you're going to do first here is we are going to do what's called bug the exam question. So we're going to look at it bit by bit, and you are going to box any command words, underline any keywords, and then have a go at the question. So we'll do the box and underlining first before you have a go. So if we look at the first question, calculate the kinetic energy of the rocket just after being launched. So you've got a lot of information at the top before it, you've got a diagram there to help visualise what is happening in this situation. So if we have a look further up, you've got the speed of the rocket just after being launched is 12 metres per second. So that's telling you speed. So that might be a key bit of information that you might want to underline. The mass of the rocket is 0.05 kilograms. So again, that's highlighted another bit of information. Now, the command word for part 1 would be the calculate, because it tells you you've got to do a calculation, so you will have to use an equation. So you would box that, and we're focusing on kinetic energy, so you would underline that. So hopefully you're already thinking, well, I need to get my kinetic energy equation and use it for this question. In the section at the top, it tells you the mass and the speed. And then for part 2, as the rocket moves upwards, it gains gravitational potential energy. You've got to state the maximum gravitational potential energy gained by the rocket. Ignore the effect of air resistance. So that word state would be your command word. So you don't need to do any calculations for this, you just need to write down what that value would be. So think about in the previous slides when we were talking about gravitational potential energy transfers into kinetic energy. The same thing happens the other way around as well. Okay, so what's the maximum gravitational potential energy that they could have for the rocket? And in part 3, another calculate question. So straight away we've got calculate, so that will be your command word to box. The maximum height the rocket will reach. Again, it gives you another bit of information to use, and you want to work at the height. So you have to think about, well, if I've got a height, which energy equation have I got that includes height? It tells me gravitational field strength, so you've only got one energy equation that includes that. Think about which equation it would be, then you'd have a go at it. So here are the key bits that you would have boxed and underlined for this question. Now pause the video and have a go, please. Okay, so we should have had a go at the questions here. Part 1, we should have got an answer of 3.6. If you're not sure how to do that, your equation you were using was kinetic energy is a half times by your mass times by your speed squared. It told you in the question that you had a speed of 12 and you had a mass of 0.05 kilograms. So you put your numbers into the equation and we should get 3.6 joules of kinetic energy. Part 2, it's your maximum gravitational potential energy. So that kinetic energy, imagine all of that is transferred into your gravitational potential energy. We're ignoring air resistance, so we're ignoring any frictional forces. So you would write the same answers you had for part 1. If you didn't get 3.6 for part 1, that's okay. If you just write the same answer that you had for part 1, you would still get a mark for that. And then part 3, you have to use your gravitational potential energy equation for this one. So gravitational potential energy is equal to your mass times by your gravitational field strength times by your height. And you would have to substitute your numbers in correctly and then rearrange to find your height. So right at the bottom there, it tells you what your substitution would have been in. So you'll get a mark for your substitution and then a mark for your correct answer. If you'd got part 1 incorrect, but then part 2 was the same as part 1 and you've carried that through, it says there you got there part 2. If you've taken that value, that's absolutely fine. You can still get 2 marks for that question, as long as you've done the correct rearrangement for it. So now we're going to speak about specific heat capacity. So there is a definition there of exactly what it is. So specific heat capacity is the amount of energy needed for 1 kilogram of a material to heat up by 1 degree C. So what that means is you'll have a certain amount of energy, so for a kilogram of an object, in order for it to increase in temperature by 1 degree Celsius. Every different type of material will have a different type of specific heat capacity. It will have a different amount of energy that it needs in order to heat up by 1 degree C. So at the bottom you've got 3 examples. You've got copper, aluminium and gold. And you can see from the values that they have different specific heat capacities. The units kind of link into it as well. So if you remember, the units for energy is joules, the units for mass is kilograms, and the units for your change in temperature, or your temperature, is degrees Celsius. So that's where those units come from. And you can look at those units to help you with the definition. So for example, for copper, it needs 385 joules of energy in order for 1 kilogram of copper to be heated up by 1 degree C. Same idea with aluminium, except it's a much higher specific heat capacity, so it needs more energy. So it needs 913 joules of energy for 1 kilogram of aluminium to heat up by 1 degree C. And then similar idea for gold, but gold's a lot lower than the other two. So gold only needs 126 joules of energy for 1 kilogram of gold to heat up by 1 degree C. And it can also be represented by the equation that's there. So your energy, so linked to your thermal energy, is your mass times by specific heat capacity times by your change in temperature. So in this example here, we're going to practice using that equation. So you will need to pick out the correct numbers from the statements above. Watch out for your command words and your keywords for this. So when a cyclist uses the brakes, the bicycle slows down. This causes the temperature of the brake pads to increase by 50 degrees C. So that's already your change in temperature. The mass of the brake pads is 0.04 kilograms. So again, that is your mass. That is another bit of information. The specific heat capacity of the materials of brake pads is 480 joules per kilogram degrees C. So that is your specific heat capacity. So you've got all the right information you need to use the equation below in order to calculate the change in thermal energy. So it says calculate this change in thermal energy of the brake pads. So you calculate would be your command word, and your keyword would be the change in thermal energy. So pause the video here to have a go at that question. Here you can see you're working out. So well done if you had to go at that question. Your energy would be equal to your 0.04, so that'll be your mass, times by your 480, which is your specific heat capacity, times by your temperature change of 50 degrees. And you should get an answer of 960 joules. So you will need to understand how to carry out this specific heat capacity required practical. In the diagram you can see a setup of this practical, and there are a few things to consider for this. I put the main key points on the left for this practical that you would need to know. So what you'd start off with doing is you'd set up your equipment, but also you would need to know what your mass of your block is. So usually we'd maybe use a 1 kilogram block. You'd measure your initial temperature using your thermometer, and then you'd set your potential difference perhaps to 10 volts, for example. Then when you are ready, you would start your stopwatch, and then you will record your temperature, current and your potential difference every minute for 10 minutes. The energy transfer that we're looking at for this is from electrical to thermal. So for this practical, what we can do is see how much energy we need in order to increase the temperature of the block. That block could be aluminium or it could be copper. In order to work out your energy, you would then use the information you have from your time. So you would also use your, you need to work out power as well. So you use power is your current times by your potential difference. Once you have that, then you can work out your energy with your power and your time. Sometimes we could potentially use what's called a joule meter, and this measures the energy directly for you. The reason we do this is so then you can use the thermal energy equation with your mass specific heat capacity and your change in temperature to then work out the specific heat capacity of the block. There is a video link at the top right there, which you can type into Google, or you can search for it on YouTube, specific heat capacity, which will be worth having a watch. Here just describes what to do with your information once you've got it. So in the previous slide I mentioned about how to calculate the power, so you've got your equation there in the first bullet point, and then how you would calculate your energy. Again, the equation is there for you. You would then plot your graph with your temperature in degrees C on the y-axis against your energy on the x-axis. And then once you're able to find the gradient of your line, you would do your 1 divided by your gradient in order to find the specific heat capacity of that block. So here we're going to look at power and work done. So when work is done on an object, energy is transferred. So you think, well, work done means there's energy transferred. So if you ever see work done, think about energy, but it's your energy transfer. So energy is being transferred from one type to another. The rate at which this energy is being transferred is called power. So power is how much energy is transferred in a certain amount of time. So if you've got a higher power, the more energy that will be transferred every second. And these can be linked by the equations that you can see there. So you've got your power is your energy transfer divided by time, or you can say power is your work done divided by time. Okay, so now we're going to practice using the power equation. So you have a motor and the lift does 120,000 joules of work in 8 seconds. So you've got calculate, so you'd be boxing the calculate word because that's your command word. The power output, so that's your key word, so you'd underline that, of the lift, the motor and the lift. And you've got the equation there for you. So you just need to decide between those two numbers at the top there, which is your work done, which is your time, and then put your numbers into your equation and calculate it. Pause the video here and have a go at that question. Okay, so this is what we should have got. So your power would be the 120,000 divided by 8. So just remember 120,000 joules is your energy transferred, which is the same as your work done. And then once you've calculated that, you've got 15,000 watts. So here's another question for you to try. Calculate the work done by the cyclist when his power output is 200 watts for 1,800 seconds. So you will have to do a little bit of rearranging for this question, but remember to write down your equation, substitute your numbers in, and then rearrange and work out your final answer. Box the command words, underline the key points, and then have a go at the question. Pause the video here, and then you go move on and have a look at the answer. Okay, so this is what we should have got. So the power is your 200 watts, your time is 1,800 seconds. So remember, your power is your work done divided by your time. So in the first line you've got 200 is equal to work done divided by your time, which is 1,800. So you get 1 mark for that. And then if you've rearranged correctly, that's where you get your second mark. So your work done would be your power times by your time, so your 200 times by 1,800, and then your work done final answer would be 360,000, and that would be in joules, and that would cover your 3 marks. So now we're going to look at efficiency. So efficiency describes how energy is transferred usefully. So for example, for a light bulb, the main energy transfers from electrical energy to light energy. So your light energy would be your useful energy. However, some of that energy may be wasted as thermal energy. So a light bulb isn't necessarily 100% efficient because not all of the electrical energy transfers into light energy. Some of that is wasted into thermal energy and into the surrounding area. We can describe efficiency using an equation where it's your useful output energy or power divided by your total input energy or power. So here's an example to have a go using that equation above. So a blender has a useful power output of 420 watts. It has a total power input of 600 watts. Calculate the efficiency of the blender. So it calculates your command word. You're looking to calculate your efficiency, so efficiency would be a keyword, and you have some key bits of information. So you need to decide which bit of information is your useful energy or power, which bit of information is your total, and then have a go at that. Pause the video here and then continue on when you have finished. So hopefully you have pointed out that the useful power output was 420 watts and the total power input was 600 watts. So for your calculation you should have done 420 divided by 600. You should have got an answer of 0.7. If you got an answer greater than 1, then you have put your numbers the wrong way round. For efficiency, if you're keeping it as a decimal, you cannot have an answer greater than 1. So just be careful with that. If you wanted to put it into a percentage, then I would multiply that decimal by 100 to get 70%. So that's something just to think about if the question asks you to put it as a percentage. If it doesn't specify, then you can do either. So this is for higher tier only. How can the efficiency of the blender be increased? So how can any energy or power input be transferred more usefully? So there's not less energy that is or power that's being wasted. And why can you not have an efficiency greater than 1 as your decimal or 100%? So pause the video here, have a little think about it, jot some ideas down, and then continue on. So here is a model response of what you might have had. So how can the efficiency of the blender be increased? So you can achieve by reducing wasted energy transfers, so more of the input energy is usefully transferred. So such as using some sort of lubrication to reduce the friction between the moving parts of the machine and increase the amount of useful energy transferred. Why can you not have an efficiency greater than 1 or 100%? This is because it is not possible to have more energy than what you started off with or more power than what you began with. This is due to the conservation of energy. So whatever amount of energy you have to start off with, you'll have the total amount at the end. So think about the start of the lesson when you had your gravitational potential energy store going into kinetic. You cannot have more energy than what you started off with. It cannot be created or destroyed. It can't just come out of nowhere. It can't just disappear. It's got to be transferred from one type to another. So now you're going to have a go at some practice exam questions with efficiency. So remember to box your command words, underline your keywords, have a look at the information that is given, and then when you are doing equation work, make sure you write down your equation first, then substitute your numbers in. Maybe have a look to see if you've got to do any rearrangements and then work out your final answer. For the first question, you don't need to do any rearranging. The second one you will, so it's important that you take those steps. Please pause the video here and then check your answers on the next slide. So these are the answers that we should have got. So for your first question, you've got your total power input is 750 watts. Your useful power output is 360 watts. So you should on your efficiency is your 360 watts divided by your 750, which would get you an answer of 0.48. You then could have multiplied it by 100 to put it as a percentage, which would have been 48%. For the second question, you have to do a little bit of rearranging, so it's important that you write your equation and substitute your numbers in first before you do any rearranging, because you'll get different marks at different points. So your first mark is for substituting your numbers incorrectly. So your efficiency here is 0.2, which is then equal to your useful power output divided by your total power input, which in this case is 2.4. You then would rearrange that, so your useful power output is going to be 0.2 times by 2.4, so that's your second mark. And then your third mark is for working out your final answer of 0.48. So now we're going to look at energy resources and uses. So here, this can be split into two columns. So you've got your non-renewable and your renewable. So your non-renewable resources are sometimes what we call finite resources. They are going to run out. Your renewable resources are sources that are not going to run out. So for example, for non-renewable, we've got coal, oil and gas. And then for your renewable, you've got a list there: solar, wind, hydroelectric, biofuel and geothermal. There are pros and cons to each of these, and you would need to identify these. For the non-renewable sources, they all cause damage to the environment through pollution. So when they are burned, they release harmful gases into our atmosphere, but they do provide a lot of energy. For your renewable sources, these cause very little to no damage to the environment, but they do not provide as much energy and can be unreliable. With unreliable, for example, solar, it must be sunny in order for us to have to gain solar energy. Or there must be at least some form of sunshine. So at night time, for example, the sun isn't there, so we are unable to use solar energy. For the wind, it's not always windy, so therefore, again, that would only be reliable if it was windy, but it's unreliable because it's not always windy. So there are examples to think about. So here is a bit of a graph interpreting information question for you to have a little go at. So you can see here, I've already bugged it for you for this one, because you've got a lot of other information that you need to take from it. So the graph gives information about the production of electricity in the UK in 2016. You've got a graph with percentage of total on your y-axis and energy resource on your x. And you've got gas, nuclear, coal and wind. The UK government signed the Paris Climate Agreement in April 2016. The agreement commits the UK to reduce the amount of carbon dioxide released into the atmosphere. So your command word here is explain which energy resources in the graph should be used to meet the UK's commitment to the Paris Climate Agreement. So you will need to pick your energy resource that you think that the UK should use to meet the Paris Climate Agreement, and tell me why that is as well. So remember, the Paris Climate Agreement is to reduce the amount of carbon dioxide released in the atmosphere. So you will have to think about, well, which energy resources release carbon dioxide, and which ones do you think that don't, and which would release the least amount of carbon dioxide. So those are things to think about for that question. Please pause the video here and have a go. So here is the mark scheme for that question. I'm going to go through it with you, so hopefully it'll make sense. This is a 4-mark question, so there are 2 levels to it. So at level 2, you would made relevant reasons, and you're given detail, and it's all logical, and so it makes sense in what you have written. So you could potentially be within the 3 to 4 marks. For level 1, you've given some good reasons, but it's not necessarily linked together, and it doesn't necessarily make sense as such, but you have made some good points. So that'll be your 1 to 2 marks. So the content you could have, you don't have to have all of these bullet points at the bottom, but this is what you could have written. So for nuclear, you have a list there of what you could have written, and the same for wind. So those were the two options that you should have chosen and explained. If you've made most of those points, then absolutely you would be in the 3 to 4 mark brackets. If you've made 1 or 2 out of either of those, then you might be in the 1 to 2 mark bracket. So now have a little try at the practice exam questions. So remember to box your command words, underline any key bits of information, then have a go.